Fältström. I'm head of now engineering, research and development. It's one of the longest titles in the world, but there's not much I can do about that. I have been working with my team and many other people at Netnod and elsewhere.
I think it's muted, yeah.
So this is better, thank you. Okay, Patrik Fältström. I'm head of the new engineering department, but also research and development as before. We have been working on developing new NTP services, which are deployed that Ragnar will talk a little bit about later. But I would like to give a little bit of background on why we have been doing this. Time is something that is actually pretty easy, and at least to start with. To have a clock, you need something that is ticking, and then you have something that counts the ticks. It's not harder than this, okay? But the problem is, of course, to have these ticks go sort of in sync. This is a picture that I took about, I think, 10 years ago in Sundblad, the Prime Minister's office in Stockholm. And you don't have to be sort of a time nerd to understand that there's something wrong in this picture. What now has happened, I checked with some people from SIDA that was in this very room last week. And someone has changed the arms on these clocks, so they are now correct, but the arms are not moving. So one of the things that I brought up with the state secretary that hosted that meeting was, is this something that you want me to fix? And they said yes. So anyway, so my challenge now, that is the next goal in this project, is to make sure that the clocks in the Prime Minister's office is actually going correct. So what is the actual problem here? Well, you have, when you talk about accuracy, you have, in reality, both accuracy and precision. And what we are trying to do is to make sure that time that is delivered, both time and frequency and phase, is both accurate and with high precision. And this is the problematic part. And the really big problem is, of course, that how accurate and what level of precision is needed. That is something that is given. The easy way of explaining this is that it needs to be more accurate and more precise than the time span between the various events. So if you look at, for example, the number of transactions that a credit card company gets, might be 1 million or thousands, hundreds of thousands or millions a second. And that means that if you want to know what order the events are taking place, you need to be much more precise than that. So one thing that we have in Swedish legislation, which is kind of interesting, is that one of the oldest laws that we're using, from 1736, is saying that if someone is selling the same goods twice, the first one that did buy the goods is to keep it. And this means that since 1736, it is important to Sweden to know in what order transactions took place. And then you have all the modern legislation in Europe, like Eurosox and other kind of things. But there are also a couple of other events that has happened in Sweden, specifically after the tragic murder of the Swedish Foreign Minister, Anna Lindh. We have a couple of procurements that have stopped early because people were running web servers on Windows systems, PCs that did not really have their clock correct. We have the video cameras that have not the time set correctly, so you don't know when the video was taken. And the interesting thing here at the end, the last bullet here, we have these fees, these road fees that has to be sort of paid here in Stockholm. That's actually a decision on, that's a tax. Okay, and what happened was that one of the time geeks that we have here in Sweden actually appealed the tax decision because he claimed that, well, I actually passed on the cheap side of a certain point in time. Can you prove at what time this actually happened? And they could not. So he got his money back and they fixed their time distribution. So now the time is actually correct on the payment systems we have. So why are we doing something new? The easy way of explaining this, at least like you see it visible, is that these are the old clocks. And on the time scale here at the bottom, you see time like 0 hours, 2 hours, 4 hours, and each one of those blips is that there is an adjustment on the rubidium clock. That's a little bit too many. And you can also see here on the left y-axis that we are sort of managed to get the time within 10 to the power minus 6 seconds. That is not good enough. So 10 years ago, some work started in Sweden to investigate whether this is good enough or not. And the conclusion, after quite a lot of work, specifically in this report from various agencies responsible for the security and stability of the society in Sweden. They said that it's actually pretty important that the Swedish system of time and frequency is more stable than what it is today. The Swedish regulator picked that up and said, we are the ones that are going to take care of this, and they have solved the problem by asking us at Netnod to please implement a new distribution system for time and frequency. We at Netnod in turn has been doing that together with SP in Borås, that actually is the one that decides what Swedish time is, with the Swedish University Network and the Royal Institute of Technology. So that's sort of the cooperation setup. It's PTS that is running the project, asking us. And Ragnar will talk a little bit more in practice. What is it we have done? This is actually this is the excerpt from the contract. So this is what PTS formally has asked us at Netnod to do. And now I would like to hand over to Ragnar. If you're interested in time, these books are actually really cool. I don't read many books, but these are fun. Specifically the last one where I've written a part of it.
Thank you. My name is Ragnar Sundblad, eller Ragnar Sundblad, säger vi på svenska. Called Ragnar by most. I've been working with implementing this system, mainly the integration. An agenda for today, then some background, and then also the services that we deliver, an overview, and we also made our own NTP server hardware for various reasons. I'll talk about that. How the time transfer between those nodes work, and our internal network, and where we're heading for the future, and hopefully some questions for the things that I didn't cover that you want to know about. I'm very interested about that. So, some background then. Yes, this is funded by the Swedish Telecom Post Authority, Post and Telecom Authority, as Patrik mentioned. It was decided to have a distributed timescale in 5 locations, and they are co-located with internet exchange points, so it's pretty safe places, but also where it's pretty accessible to the telecom networks. Each node is autonomous in the sense that it itself collects all the timing data that it needs from other nodes and from other sources such as SP, and makes its own calculations and adjusts its timescales accordingly. If it can't get any data, if it would be isolated for some reason, it will just tick along and can do that with quite some both precision and accuracy for quite a time, weeks or months. SP, as Patrik mentioned, creates the national timescale, Swedish national timescale. Our timescales are traceable to UTC SP, and UTC SP is also traceable to other timescales all over the world. So the services we deliver, there is some live data available over the internet. The generally available time service is NTP, of course. We have it using unicast, which is good for more static setups, more advanced setups. If you care, I would say, about time, use unicast. We also have an anycast address, which directs the client to the closest time node, which is good for easy setup, for getting people over the threshold to actually get some time from somewhere, and also for roaming setups. It can also do authenticated NTP. We have time comparisons for our timescales compared to UTC SP and some other switch time labs. There is time transfer data to be used with navigation satellite systems such as GPS. With this data and a good clock and a suitable receiver, anyone can make their own timescale that's traceable to our system, which is traceable to UTC-SP. The system also exports internal measurements, clock steering data, and operational data. And then there are physical signals which you need to be on site. You need to get a cable to our time node to get those. There is PTP, or 1588 V2, over 1 gig Ethernet, and there is synchronous Ethernet on that one. We have an E1 clock at 2048 kHz, 2 MHz, which one you prefer. And we also can deliver 1 PPS, 1 pulse per second, 5 MHz, 10 MHz analog signals, if anyone would want that. So
what's the precision of those signals?
The precision. That's a very, very good question. It depends on the needs, I'd say. We have one need that's actually formulated is for the telecom networks. The cellular telecom networks, they want tone nodes to not be out of phase for more than 800 nanoseconds. So that must be our worst case ever, what we should never do worse than. When everything is working properly, we are probably within much less. If you promise to forget that I told you, the regulation is within single-digit nanoseconds. We also have some offset errors because of calibration errors. That's probably also within single-digit nanoseconds. But that's not what we promised. That's just how it behaves when everything works perfectly, which it generally has so far. Was that clear enough? Was that fast enough? Okay, thanks. So an overview of one of those 5 time nodes. There are 2 node halves, which are, in most senses, they're redundant, so that a node can run and deliver time with an entire half down. There are several interconnections between the 2 node halves, so that even for example, one of the clocks break, most other things should run normally in both halves. At the bottom, we can see the 2 atomic clocks, the beige things with clock indicators on them. There is a measurement and control system. The measurement devices feed data to control computers. That measures the timing on all the components in the node and should see that they behave properly. They are within limits. The control system also makes the time calculations and steer the timescales, the output timescales, so that the timescales in the entire system, all the timescales in all the nodes, follow each other. There are NTP servers in one of the black boxes in the top there. We'll get back to those. There's an PTP 1588 sync E generator and E1 clock generator. Oh, there it was. Sorry. There's the NTP servers and 1588. and E1 clock generator. We have a satellite receiver for time transfer between the nodes and from others, from SP for example. There's a backbone network that connects nodes. It's used both for data transfer and for time transfer between the nodes. We have data I machines that serve the data to the internet and also fetch data from the internet, from other nodes and from others. And there is backup power, of course. In these sites there are redundant UPSs and diesel generators. And in addition, the clock equipment, the stuff at the lower half here, is connected to another 3 days of battery. We really don't want to lose time, because then we have a lot of work to get back on time again. So the internal structure of Node, we have two cesium clocks. There are two node halves. The upper part of this slide is kind of one half, and the lower part is the other half. So we have the cesium atomic clocks. We use those as oscillators. They generate 5 MHz, very stable signal, but they don't necessarily follow what SP thinks the natural time scale is. So we have to offset those a bit, just a tiny bit. So we have the frequency and phase offset shift machine. Those are the ones that we steer to generate the actual time scales. Then we have output amplifiers, and the timing 0 point of the node half is defined as at the output of the amplifiers. And those are both in double M, that's left and right half of the node. Most internal signals here are 1 PPS, 1 pulse per second on 5 MHz or 10 MHz on coaxial cables. As you can see, there are actually 2 generated timescales from each node, one from each node half, so the entire system has 10 timescales in total out, but they're steered to follow each other. We have a satellite navigation system receiver that receives the American GPS system, the Russian GLONASS system, and the European Galileo system that's currently in deployment. I think they have 10 satellites up now, or something like that. This is used for the high precision time transfer with the other nodes and with SP and other time labs. We also have a fiber transfer network, fiber time transfer network, using PTP between the nodes. The NTP service and the PTP service are connected to both timescales, so if we would lose one clock for some reason, we could still operate those as before, or normally. And we have data services computers that hand out the data I mentioned before. Everything in this picture is also connected to the measurement system, not the data computers, but all the clock equipment, so that we can track what they're doing. The NTP server, we actually created our own hardware NTP implementation in an FPGA. That's a programmable logic device. The idea is that it should be hard to DDoS the service. We want the bottlenecks for the DDoS attack to be elsewhere in the network and not at the NTP service. So it's designed to handle 4 times 10 gigabit NTP traffic at full wide speed. It handles both IPv6 and that other thing. It's quite secure, and it's a minimalistic NTP server that runs entirely in hardware. No NTP packets ever go into the host computer. It's not, we believe, susceptible to the NTP amplification attacks, since it does not respond to any controlled packets, and every packet that leaves it is a response to an incoming packet of at least the same size. So it should be quite meaningless to use these as for amplification. It can do authentication using symmetric keys. We had to make our own interface card to get 1 pulse per second and 10 MHz signals from left and right node off into it. And there are also outputs so we can measure what the local clocks on the card is doing. That's the only piece of hardware that we have had to develop in this project. Everything else is off-the-shelf things. The FPGA source is open source, so it's free for anyone to implement their own. You can create your own one of these. When we actually have seen some interest from some other countries. Okay. We use several methods in parallel for the time transfer between the nodes. And at any one time we use the best method available. The highest precision method at the top here is we use both GNSS, the Global Navigation Satellite System, systems with some measurement data that measured the trajectories that the satellites turned out to have in their flight path. That's what was measured after the fact. The problem with that is that this data isn't available until after about 17 hours after the day that was measured. So we can't really use that for real-time measurements, only for long-term measurements and adjustments. We also have satellite time transfer in a more normal mode, where we use the calculated or estimated trajectories that were estimated beforehand. This is what is typically used for the daily time transfer for short-term adjustments. We have the fiber backbone network which uses PTP. It gives a little less precision, but not much, in the order of nanoseconds. In an extreme situation, if one of these nodes really would lose all contact with the outer world, we don't have any satellite system or any fiber system, we would have to fall back to put an atomic clock in the car and drive around to adjust them every few weeks or something like that. We just hope that will never happen. If the methods for some reason disagree, we don't do anything, because then there's probably something wrong. So we just sound an alarm and let the human being take a look at it. We have an internal fiber network that's used for time transfer and data transfer, as I mentioned. It uses dedicated wavelength channels in the Swedish Research and Education Network, SUNET. For time transfer, as I said, it's mainly a backup just because of the lower precision. We would of course prefer to use the fiber network instead of relying on foreign satellite systems. In this map, we also have we have an extra test and development node at the SUNET premises. So there actually are 12 timescales, but only 10 officials. Yes. And for the future, we would like, as I mentioned, to use our own time transfer over fiber and have that as the highest precision method. So we would probably switch to coherent optics and do away with all the timing asymmetry and variation that we get from the current fiber optical networks, which has dispersion and compensation fiber roles. Which introduce just asymmetries, timing variations there are in traditional, or in all fiber networks, of course. We looked at 100 gigabit systems or possibly analog systems, but these systems are currently more of the research stage. investigating storing all the data in a distributed hash table database so that it would be available near real time for anyone that's interested, and perhaps also using it as the internal data transfer method. There are some ideas about develop the authentication of the time data tied to the actual calibration of the equipment. And we'd like to have more software methods to automatically handle operational problems. We don't really know what those are yet. We haven't had many problems. So it's kind of hard to define that. But we want it to be as autonomous and automatic as ever possible. Thank you. And now I hope for some questions. Yes, please.
Yeah, what time is it?
You have 10:27 and something. I'm never sure.
Is this a Stratum 1 or 2?
Can we use microphones? Since we're streaming, it's good if you give me other questions as well.
Thanks, everybody from SSH. Is this Stratum 1 or 2?
They are Stratum 1 in every aspect. Yeah, when we were announcing this to the NTP pool guy, they wondered, "Oh, you really want to put them in the NTP pool since they are Stratum 1 machines? They shouldn't be talked to by anyone." But these are designed to be the interface to everyone. That's the idea. Yes.
At Netnod, Patrik showed this graph of the old system. Do we have any graphs from the new one, so we know the precision, or is it too young to have any graphs yet?
Actually, they aren't exported. We have internal data, but that's one of the things that's on our rest list, to export nice graphs and everything. Actually, we haven't even decided on all the data formats for all the data yet. It's logged internally, but it's not exported yet.
So can you tell us anything about the precision? Is it 10 times better or 50 times better, or
compared to the old ones? I'm sorry, I don't really know what precision the old one. I haven't studied that. What? -6 or -seconds. Okay, then we should have 10 to 100. Hopefully. Yeah.
Well, before we let Ragnar leave the stage,
I just want to say one more thing. For those of you that want to use the NTP service, if you go to www.ntp.se, you see a web page with information on the NTP service they can use. And if you just configure your NTP client to fetch time and talk NTP with ntp.se, then everything will work for you.
And maybe I say, when we talk about, if you only see 4 NTP servers there, or 4 sites, it's because you have to forget again, the Luleå site is still not yet in service. It will be soon.
any other questions yet?
Do you see downstream quote-unquote use of this? Court cases, who is keeping track of how society is making use of this increased precision? I'm sure it's not you guys, but someone should.
SP is keeping track of it. We're also in discussion with what is called Finansinspektionen in Sweden. We also, of course, have good cooperation with the regulator. When we also have discussions with, for example, the Swedish police. And every time you see something that is called traceable time, spårbar tid in Swedish legislation or recommendation, that is something that is then supposed to use time from SP, and we are the one that distribute that. So that's how it's managed. Together with the regulator, we also just want to inform all the mobile operators here in the room that your formal regulative contact at the mobile operators, which of course is probably not you guys, they have got a letter from the regulator calling to a meeting in April. And I'm happy to ensure that you who actually should be at the meeting also get called. So just let me know, ping me, and I'll make sure that you get the invitation.
Okay, well, before we let Ragnar go, because this has been a big project for us, and Ragnar has played a key part in this role. Patrik has a
Yes,
little
I have
gift to give to
we
Ragnar.
have this sort of, we try to do this, maybe I should stand over here. We try to, together with Ragnar, we try to do this sort of speaking gift thing, and no, it doesn't have an NTP on the back. But Ragnar, thank you very much for all the help with this project, and I look forward to continue working together with you and the others as well. So, welcome. So he got a robot clock. He has to ensure that the time is correct by inserting battery and sort of, or at least I hope that you can run this clock better than the Prime Minister can run his. Thank you very much, Ragnar, and thank you. One more thing. Oh, I see many people here, old consultants, also employed by Netnod, that have been involved in the NTP project in one way or another. Can you please stand up? Ulf, Mem, Kai, Jürgen. You see, many of them, Stefan. Thank you very much, all of you, for all the help. We have been working on this for a couple of years, and now we're here. Thank you.